From the silent depths beneath the French-Swiss border, something impossible happened. No alarms screamed, no lights flashed red, no sirens tore through the underground corridors, just the low hum of machines that never sleep. On an ordinary Tuesday morning, a physicist sat alone in the control room of the Large Hadron Collider, staring at her screen. Her coffee had gone cold beside her. The numbers on the display refused to make sense. They were wrong. Not slightly off. Not within the usual margin of error. They were wrong in a way that should not be possible. She blinked hard, refreshed the data, and checked again. Same result. Her stomach dropped. For a long moment, she simply stared, the weight of what she was seeing pressing down on her chest. Then she picked up the phone. She called her supervisor. Her voice was quiet, almost too calm. "You need to see this." Minutes later, the room filled with people. No one spoke at first. Senior physicists crowded around the monitors, faces lit by the glow of graphs and collision data. Someone whispered, "Run it again." They did. The anomaly remained. A tiny deviation in how a particle had decayed. Something the rulebook of physics said should never happen. That moment has repeated itself several times over the past decade at CERN. Different experiments, different teams, different particles. Same quiet shock in the control room. The kind of shock that makes seasoned scientists question everything they thought they knew about reality. Welcome to Cosmo Depth. Today we go deep inside CERN into the heart of the world's most powerful machine, where the rules that hold the universe together appear to be breaking. If you're the kind of person who lies awake thinking about what we're really made of, what holds existence in place, and what might be hiding just beyond our understanding, then stay with me. This one's going to stay with you. This one's. Imagine the longest tunnel you have ever seen. Now, make it circular. Stretch it until it's 17 miles around, wide enough to loop an entire city inside. Bury it 300 feet underground, beneath farmland and quiet villages on the border between France and Switzerland. Line every inch with superconducting magnets cooled to temperatures colder than outer space. Create a vacuum inside so perfect it has less air than the surface of the moon. That is the Large Hadron Collider, the most complex machine humans have ever built, and right now, it is whispering something terrifying. For decades, we believed we had the universe figured out, not perfectly, but close enough. We had a framework called the Standard Model. It described every known particle, every force that matters at the smallest scales. It predicted things before we could even detect them. And time after time, when our machines finally caught up, reality matched the prediction exactly. Scientists called it the most successful theory in the history of science. It felt complete, bulletproof. Then the cracks started to appear. Not loud explosions in the data, not dramatic flashes on a screen, just small, quiet, persistent numbers that refused to line up. Tiny deviations that, in the world of particle physics, scream louder than any siren ever could. One of those moments happened in the LHCb experiment, the detector built specifically to study beauty quarks. Another came from a completely different machine across the ocean, measuring something as familiar as a Muon. And together, they point towards something that should not exist. A possible fifth force of nature, something beyond the four forces we thought governed everything. But before we get there, you need to understand why a single misplaced decimal point can make a physicist feel sick to their stomach. Picture your hand in front of your face. It looks solid. It feels solid. But zoom in far enough and it's mostly empty space. Atoms, with electrons orbiting nuclei like distant planets, and those nuclei made of protons and neutrons, and those made of quarks, held together by forces we can describe with elegant equations. The Standard Model gave us those equations. It told us how particles should behave, how they should decay, how often certain interactions should happen. For 50 years, it was right almost every single time, until it wasn't. Deep underground, protons race around that 17-mile ring at nearly the speed of light. They smash together 40 million times per second. Each collision is like recreating a fragment of the Big Bang. Detectors the size of buildings record everything. Millions of gigabytes of data every day, and somewhere in that ocean of information, patterns emerged that no one expected. A beauty quark decaying at the wrong rate. A muon behaving as if an invisible hand was nudging its magnetic moment. Small violations of rules that were supposed to be absolute. Scientists are careful. They check everything twice, 3 times, 100 times. Equipment failure? Calculation? Error? Statistical fluke? They ruled out possibility after possibility. The results stayed. And that is when the real unease began. Because if the Standard Model is wrong, even a little, it doesn't just mean we update a textbook. It means the foundation we built our understanding of reality on has a hidden flaw. It means there might be physics we have been completely blind to. A new force, new particles, rules we never suspected. It means the universe might be far stranger than we imagined. And it means that everything we think we know about how matter holds together, why anything exists at all, and what the future of our cosmos looks like, might need to be rewritten. That physicist in the control room that Tuesday morning wasn't just looking at bad numbers. She was looking at the first thread of a story that could unravel everything. And we are only at the beginning. But to truly feel why this matters, we have to go back to the rulebook itself, how it was built, why we trusted it so completely, and where it started to fail. The story gets even more unsettling from here. Scientists spent roughly 50 years piecing together the Standard Model. Imagine a group of the brightest minds on the planet sitting around tables covered in equations, arguing late into the night, building something piece by piece like the most intricate puzzle ever attempted. They weren't guessing. They were following the data, predicting particles that no one had ever seen, and then watching machines confirm their predictions, years or even decades later. It was breathtaking. The model describes 12 fundamental particles of matter and 4 forces that control them: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. It explains how atoms form, how stars burn, how radioactivity works, and why certain particles decay exactly the way they do. For most of a century, every single experiment agreed with it. The Higgs boson was the final missing piece. Predicted in the 1960s, finally discovered at CERN in 2012, after decades of searching. Peter Higgs himself sat in the auditorium that day, an elderly man wiping tears from his eyes as the announcement came. The room erupted, champagne flowed. It felt like the end of an era. The book was finally complete. But even the people who built it knew, deep down, that it wasn't the full story. The Standard Model has no explanation for gravity at the quantum level. It says nothing useful about dark matter, the invisible substance that seems to hold galaxies together. It cannot tell us why the universe is made of matter instead of pure light, after the Big Bang should have wiped everything out in equal amounts of matter and antimatter, These were known gaps. Scientists assumed they would fill them later. Then the anomalies started showing up. Not gaps. Direct contradictions. The first real warning sign came from the LHCb detector. Beauty quarks, also called bottom quarks, are heavy, short-lived particles produced in the high-energy collisions inside the LHC. They live for about a trillionth of a second before decaying into lighter particles. The standard model predicted exactly how often each type of decay should happen. The rates were supposed to be precise, almost like clockwork, but the data refused to cooperate. Beauty quarks were decaying into electrons and muons at slightly different rates. According to the model, those rates should have been identical. Lepton universality, one of the core principles of the theory, said so. Electrons and muons are supposed to behave the same way in these interactions, differing only in mass. Yet the numbers kept showing a preference. One path happened more often than it should. The team checked everything: calibration, background noise, analysis methods. They ran the experiment again and again. The deviation persisted. It wasn't huge in everyday terms, but in the world of particle physics, where precision is measured to many decimal places, it was enormous. A crack in the foundation. Scientists around the world felt the ground shift beneath them. Some tried to explain it away. Others started drawing new diagrams on whiteboards, adding hypothetical particles that could interfere with the decays. Leptoquarks, Z-prime, bosons, things that would bridge quarks and leptons in ways the standard model forbids. But that wasn't the only crack. Far away, at Fermilab in Illinois, another experiment had been quietly running for years. They were measuring the magnetic moment of the muon, a heavy cousin of the electron that rains down through our atmosphere constantly. The standard model predicted this value with incredible accuracy after decades of theoretical work. The experiment was supposed to confirm it. Instead, it produced a result that disagreed with the prediction. The difference was tiny. But again, in this field, tiny means everything. The muon was behaving as if something invisible was tugging on it, adding an extra push that the known forces could not account for. Teams spent years double-checking the massive superconducting magnet they had transported across the country. The result held. 2 completely different experiments, 2 different particles, 2 quiet rebellions against the rulebook. And physicists began to whisper the same question in control rooms and seminar halls. What if these aren't isolated glitches? What if they are all pointing toward the same hidden truth? A truth that suggests there is physics beyond the standard model. A new force operating in the shadows. A fifth force that has been influencing particle behavior all along. Too weak or too subtle for us to notice until we looked with godlike precision. The house of physics had stood strong for decades. Every brick checked and rechecked. But now, on a perfectly still day, one wall had started to vibrate. And the deeper scientists looked, the more walls showed signs of movement. This wasn't supposed to happen. Not after the triumph of the Higgs discovery. Not after so many years of perfect agreement. The celebration of 2012 now felt like the calm before a storm. Teams that had planned to move on to other projects found themselves pulled back in. Funding proposals were rewritten. Old notebooks were reopened. The quiet confidence that had defined the field for a generation began to fracture. What if everything we thought was settled is only part of a larger, stranger picture? The beauty quark results kept improving in significance. More data came in. The deviation refused to disappear. Meanwhile, the Muon anomaly grew stronger with every new analysis. And somewhere in the background, other small inconsistencies in W boson mass measurements and rare decays started to look less like noise and more like a pattern. Scientists are trained not to jump to conclusions. They demand 5 sigma certainty before claiming a discovery, odds of less than 1 in 3.5 million that it's random chance. Several of these anomalies were approaching that threshold. Not quite there yet, but close enough to keep people awake at night. One veteran physicist compared it to standing in a beautiful cathedral you helped design, only to notice faint cracks running through the stone that no one else seems to see. The building still stands. The lights still shine. But you can't unsee the cracks. And once you see them, you start wondering what is on the other side. That question leads us straight into one of the most puzzling anomalies of all, the one involving beauty quarks and the strange preference they show when decaying into different types of particles, a preference that should not exist. But before we go there, picture this: a detector buried underground, stretching the length of a school bus, designed like a giant telescope, pointed at the spray of particles coming from collisions. Billions upon billions of events recorded. Hundreds of scientists from dozens of countries poring over the data, checking each other's work, arguing in seminar rooms, refusing to accept easy answers, all of them trying to understand why the universe is whispering back, and what it might be trying to tell us. The story is only getting started. The real surprises are still ahead. Now, let's step inside the LHCb cavern, one of the most specialized detectors ever constructed at CERN. It doesn't surround the collision point like a giant sphere the way some of the other detectors do. Instead, it stretches out in one direction like a massive telescope, carefully positioned to catch the spray of particles that shoot forward along the beamline. Beauty quarks don't fly out randomly. They tend to travel in specific directions, and LHCb was built to catch them with maximum precision. The detector itself is a marvel of engineering, 65 feet long, layered with different technologies stacked one after another. The innermost layers track the paths of charged particles with incredible accuracy. Further out, other layers identify what those particles actually are, energy measurements, and on the outside, Muon detectors that can see through material that stops almost everything else. This setup exists for one main reason: to study beauty hadrons, particles containing that heavy beauty quark. These quarks are special. They live just long enough, about 1.5 picoseconds, to travel a tiny but measurable distance before they decay. That short flight leaves a visible track in the detector, allowing scientists to tag them clearly amid the chaos of millions of other collisions. Over the years, LHCb has recorded trillions of collisions and identified hundreds of billions of beauty quark decays. The statistical power behind this dataset is staggering. When a deviation appears here, it's almost impossible to dismiss as random noise. The collaboration includes over 1,000 scientists from institutions across the globe. They check and recheck each other's work with ruthless precision. Results that survive this gauntlet carry serious weight. And one particular measurement shook the entire community. The standard model insists on something called lepton flavor universality. Electrons, muons, and tau particles, the 3 generations of leptons, should experience the fundamental forces in essentially the same way. Same charge, same interactions, only their masses differ. For the specific decays LHCb was studying, the model predicted that beauty quarks should decay into electrons and muons at exactly the same frequency once mass effects are accounted for. Reality disagreed. The decays into electrons happened more often than those into muons. The difference was small in absolute numbers, but statistically significant. The team published a result at around 3.1 sigma, strong enough to demand attention, but not yet a formal discovery. Then they collected more data, updated the analysis. The signal shifted slightly, but refused to vanish completely. Other decay channels showed similar inconsistencies, multiple independent measurements, multiple teams looking at the data from different angles. The pattern kept pointing in the same direction. Something was treating electrons and muons differently, something the standard model had no room for. Imagine the tension in those analysis meetings. Young researchers presenting slides while senior physicists leaned forward, asking sharp questions. Whiteboards filled with possible explanations. Late nights spent rerunning simulations. The quiet fear that this might be the moment the entire framework begins to crumble, mixed with the electric excitement of possibly being on the verge of something revolutionary. One theorist later described it as watching a perfectly built ship suddenly list to one side in calm waters. Everything looks fine from a distance, but the tilt is undeniable. You start checking for hidden leaks. What could cause such a violation? One leading candidate is a hypothetical particle called a leptoquark, something that could act as a bridge between quarks and leptons, families the standard model keeps strictly separate. Another is a new heavy boson, a Z prime particle with unusual couplings that prefers one generation of leptons over another. Either possibility would represent physics beyond the standard model. Either one would force theorists to rewrite large sections of the rulebook. And here is what makes it even more compelling. This anomaly doesn't stand alone. It connects to the muon magnetic moment discrepancy measured at Fermilab. Both suggest new interactions that single out muons in particular. Both hint at something reaching into the subatomic world from outside our current understanding. Scientists spent months, then years, debating whether these were real signals or sophisticated illusions created by incomplete calculations or subtle detector effects. Independent groups reproduced the analyses. Some results softened with more data. Others held firm or even strengthened. The overall picture remained uncomfortable. Meanwhile, in quiet corners of theoretical physics departments, new models began to emerge. Papers with titles that would have seemed absurd a decade earlier. Models with extra forces, extra dimensions. New symmetries waiting to be discovered. The kind of work that happens when the old map no longer matches the territory. But perhaps the most disturbing part is what this means for our understanding of the early universe. If these new influences exist, they might have played a crucial role in the first moments after the Big Bang, shaping why matter won out over antimatter and allowing our existence in the first place. The tiny surplus of matter that became everything we see might not be explained by the standard model alone. It might require this hidden physics. The LHCb team kept working. More data, better techniques, deeper analysis combining multiple decay channels. The inconsistencies didn't vanish. If anything, the case grew more intriguing as different measurements reinforced each other in subtle ways. Senior physicists who had spent their careers defending the completeness of the standard model now found themselves in the strange position of hoping the anomalies would disappear while simultaneously being fascinated by the possibility that they wouldn't. Because if they are real, we are standing at the edge of a new chapter in physics. A chapter that might finally explain the gaps we have lived with for so long. Dark matter, matter-antimatter asymmetry, the true nature of mass and force, or it might reveal something even more profound, something that forces us to rethink what reality actually is. The beauty quark has more to tell us. Its strange behavior is only one piece of a larger puzzle that includes the restless muon and hints of forces we have never directly observed. And the next part of that puzzle takes us across the Atlantic to a ring of superconducting magnets in the flat fields of Illinois, where a particle that passes through you every second of your life decided to misbehave in a way no one predicted. The Muon was about to deliver its own surprise. And when it did, the conversation in the physics community grew even louder. The walls weren't just vibrating anymore. They were starting to reveal what lay behind them. The muon was about to deliver its own surprise. Muons are everywhere. Right now, as you listen to these words, roughly 10,000 of them are passing through your body every single minute. They come from cosmic rays slamming into the upper atmosphere about 30 miles up. High-energy particles from deep space collide with air molecules and create a cascade of secondary particles. Many of those are muons, heavy cousins of the electron, carrying the same negative charge but 200 times more massive. They travel near the speed of light, passing through buildings, through you, through the ground, almost without interacting. Ghost bullets. You cannot feel them. They leave almost no trace. Yet scientists have learned to use them as exquisite precision tools. A muon behaves like a tiny magnet. It has a magnetic moment, property that makes it respond to magnetic fields in a very specific way. The standard model predicts exactly how strong that magnetic moment should be, down to extraordinary precision after decades of theoretical calculations involving virtual particles and quantum loops. The value is so well calculated that it stands as one of the great triumphs of theoretical physics. So when an experiment set out to measure it with even higher accuracy, everyone expected confirmation. Beautiful agreement. Another victory for the model. What they got instead was a discrepancy. The experiment at Brookhaven National Laboratory in New York produced a result that did not match the prediction. The difference was small, but it was consistent and in the same direction every time they measured. Something was giving the muon an extra push, an additional contribution to its magnetic moment that the known particles and forces could not explain. The physicists involved proposed a simple idea at first, maybe new physics, something beyond the standard model interacting with the muon during its brief lifetime. A new particle or a new force adding that tiny extra effect. But one experiment, no matter how careful, is never enough. They needed confirmation, so they moved the entire experiment to Fermilab in Illinois. The heart of the setup was a massive 50-foot wide superconducting magnet weighing 17 tons. Moving it was an engineering saga worthy of legend. They could not tilt it more than a fraction of a degree, or the delicate coils inside would shift. They could not fly it. They could not cut it apart. So they built a custom transport vehicle and drove it slowly across the country at 3 miles per hour, day and night, avoiding overpasses and sharp turns. Crowds gathered along the route to watch this scientific treasure roll through their towns. It took 35 days. when it finally arrived safely, the real work began. Years of calibration, testing, and data collection in a new facility with even better control over systematic errors. The result, when it finally came, sent ripples through the entire field. The discrepancy was still there, stronger, more convincing. The muon's magnetic moment refused to match the standard model's prediction, and the direction of the deviation suggested something coupling more strongly to muons than to electrons. This was not an isolated curiosity anymore. It connected directly to the lepton universality violation seen at LHCb. Both pointed toward new physics that treats the different generations of leptons differently. Both suggested a hidden influence operating in the subatomic realm. Imagine the moment the latest Fermilab results were presented at a seminar. The room full of physicists, some leaning forward, others scribbling furiously in notebooks, questions flying back and forth, the cautious optimism mixed with genuine surprise. For many, this was the moment they allowed themselves to believe something genuinely new might be happening. Theorists immediately went to work. One popular explanation involved a new particle called a muon-philic boson, something that interacts preferentially with muons. Another involved leptoquarks again, those hypothetical hybrids that could link the quark and lepton sectors. Each model offered a way for new forces to sneak into the processes without contradicting everything we already know. But the implications run much deeper than just fixing a few numbers. If these anomalies are real, they might help explain one of the greatest mysteries in all of science: why the universe contains any matter at all. In the first moments after the Big Bang, matter and antimatter should have been created in equal amounts. They should have annihilated each other completely, leaving behind nothing but energy. Instead, a tiny imbalance existed. For every billion antimatter particles, roughly 1,000,000,001 matter particles. That 1 in a billion surplus is everything. Every star, every planet, every living thing, including you, is made from that leftover matter. The standard model can produce a small amount of this asymmetry through a mechanism called charge parity violation. But the amount it predicts is far too small, billions of times too weak to explain the universe we actually see. Beauty quark decays were supposed to help reveal stronger sources of this violation. Instead, they showed something even more puzzling. The anomalies suggest that whatever produced the matter surplus in the early universe might still be leaving faint traces today, visible only in the most precise experiments ever performed. A hidden force or new particle active in the first fraction of a second after the Big Bang, now manifesting as these small deviations in decay rates and magnetic moments. That possibility is both exhilarating and deeply unsettling, because it means the story of why you exist might involve physics we have only just begun to glimpse. Physics that lives outside the comfortable boundaries of the standard model. Physics that could rewrite our understanding of the very first moments of existence. Meanwhile, back at CERN, the search continues. The LHC is being prepared for even higher energies and more intense collisions in its next run. Detectors are being upgraded, analysis techniques sharpened. Teams are hunting not just for confirmation of the existing anomalies, but for direct evidence of the new particles or forces that might explain them. Some nights in the control rooms, when the data starts coming in fresh, you can almost feel the tension. Young postdocs huddled over laptops, senior researchers pacing quietly. everyone aware that the next batch of collisions might bring clarity or deepen the mystery. And through it all runs a thread of profound human drama. Careers built on the standard model now face the possibility of revision. Decades of work suddenly sitting on uncertain ground. Yet instead of fear alone, there is also excitement. The thrill of standing at the frontier. The chance to be part of something historic. One physicist who has spent years on the Muon experiment described the feeling as similar to explorers mapping a new continent. You think you know the shape of the land from a distance. Then you push through the trees and discover mountains no one suspected were there. The mountains are rising. The W boson mass measurements have added their own layer of intrigue. Earlier hints suggested the W boson, a carrier of the weak force, might be slightly heavier than predicted. That result caused its own storm of debate, with some groups confirming and others questioning the analysis. Whether or not it holds, it contributes to the growing sense that multiple pieces of the puzzle are shifting at once. All of these threads, beauty quarks, muons, possibly W bosons, seem to pull in the same direction. Towards something new, something that treats different particles differently. Something that might connect the quark and lepton worlds. A fifth force. Not the kind you feel every day. Not gravity pulling you to the ground or electromagnetism powering your devices. A subtle force, perhaps operating over very short distances. Perhaps extremely weak at ordinary energies, but capable of influencing the behavior of particles in ways our current model cannot capture. If it exists, it would slot into the hierarchy somewhere between the known forces. It might help explain dark matter. It might offer clues about unification. It might even influence the stability of the vacuum itself. But we are getting ahead of ourselves. Because before we confront the deepest existential questions, we need to understand how these anomalies connect to the most personal mystery of all. Why there is something rather than nothing. Why matter one. Why you are here listening to this right now instead of the universe remaining an ocean of pure energy and light. The beauty quark experiments were designed in part to hunt for answers to that question. The muon results may be telling us where to look next, and the possibility of a new force brings everything together in ways that are only beginning to come into focus. The walls are still vibrating, but now we can start to see the shape of what might be causing it. And that shape is far more extraordinary than anyone dared imagine even a few years ago. The journey into the hidden layers of reality is far from over. In fact, it feels like we have only just stepped through the first door, and what lies beyond may change everything we think we know about the universe and our place inside it. The journey into the hidden layers of reality is far from over. In fact, it feels like we have only just stepped through the first door. And what lies beyond may change everything we think we know about the universe and our place inside it. While the beauty quark and muon anomalies were capturing attention, another measurement quietly entered the conversation. This one involved the W boson, the heavy particle that carries the weak nuclear force responsible for radioactive decay and the fusion processes that power the sun. For years, the mass of the W boson had been measured with increasing precision. The standard model made clear predictions. Then a large collaboration released results suggesting the W boson was slightly heavier than expected. The deviation was small in ordinary terms, but significant enough in the world of high-precision physics to cause heated debate across laboratories worldwide. Some groups confirmed aspects of the finding. Others questioned the complex analysis methods required to extract such a precise mass from trillions of collisions. The scientific community did what it does best: argued, reanalyzed, and pushed for more data. Whether the final verdict lands on the side of new physics or refined measurement, the episode added yet another layer to the growing sense of unease. Multiple independent hints from different particles, different detectors, different continents, all subtly pointing away from the comfortable predictions of the standard model. This is when the idea of a fifth force stopped being a fringe speculation and started appearing in serious theoretical papers and late-night discussions among leading physicists. What would a fifth force even look like? It would not be something you feel in daily life. Gravity holds planets in orbit. Electromagnetism lights your world and binds atoms. The strong force glues quarks inside protons. The weak force governs certain decays. A fifth force might be far weaker at the scales we experience, perhaps operating only over tiny distances inside atomic nuclei, or influencing specific types of particles more than others. It might be carried by a new type of particle, something like a Z prime boson that couples differently to muons than to electrons. Or a family of leptoquarks, exotic objects that can transform a quark directly into a lepton and back again, something strictly forbidden in the current model. Picture a leptoquark for a moment, a single particle that bridges two entirely separate families in the standard model. Quarks, which make up the protons and neutrons in every atom of your body, and leptons, like the electrons surrounding them. In the standard model, these families do not mix directly. A leptoquark would break that rule, opening new pathways for decays and interactions. It would be like discovering a secret tunnel connecting two wings of a house you thought were completely isolated. If such particles exist, they could have been produced in the extreme heat of the early universe, influencing the delicate balance between matter and antimatter. They could still be leaving faint fingerprints in modern experiments, visible only because we are now looking with unprecedented sensitivity. The possibility is tantalizing, and it connects everything. The lepton universality violations at LHCb, the muon magnetic moment at Fermilab, the hints from W boson mass. All of them could be shadows cast by the same underlying new physics, a single new force or set of particles reaching into our measurements from a deeper layer of reality. But here is where the story turns personal, because understanding these anomalies may hold the key to the most profound question of all. Why does anything exist? Go back to the first second after the Big Bang. The universe was a seething fireball of energy converting into matter and antimatter at incredible rates. For every particle of matter, an antimatter counterpart should have been born. When matter meets antimatter, they annihilate in a flash of pure energy. Equal amounts should have cancelled each other out completely, leaving a universe filled with nothing but light. Yet here you are. Stars exist, planets exist, life exists, matter won. That victory was razor thin, roughly one extra matter particle for every billion antimatter particles. That tiny surplus is the reason for everything we see. The standard model can generate a small amount of this asymmetry through known charge parity violation, but calculations show it is nowhere near enough, billions of times too small. Beauty quark experiments at LHCb were built in part to search for stronger sources of this violation. The anomalies they found, the preference for certain decays, might be indirect evidence of new physics that was active in the early universe, creating the imbalance we needed. The muon results point in a similar direction. Something new interacting differently with different particles could have tipped the scales in the first moments of creation. A fifth force, active when the universe was still hot and dense, might have been the deciding factor that allowed matter to survive. Think about that for a moment. The reason you can stand here, think, feel, and wonder about the cosmos might trace back to subtle interactions involving hypothetical particles we have never directly seen. Forces so faint they only reveal themselves in the most sophisticated machines ever built. It is humbling. It is awe-inspiring. And for some physicists, it is quietly terrifying. Because if our existence depends on physics beyond the standard model, then the model we trusted for generations was never the complete picture. It was only the visible tip of something much larger and stranger. And that larger reality might contain surprises we are not prepared for. Some theorists have begun exploring connections between these anomalies and the stability of the vacuum itself. Our universe might exist in what physicists call a false vacuum, a metastable state that is not the lowest possible energy configuration. A strong enough nudge or certain high-energy events could trigger a transition to a true vacuum, a bubble expanding at the speed of light that would rewrite the laws of physics and erase everything in its path. The thought is sobering. Our entire cosmic history, all of human achievement, every memory and hope, could be wiped out instantly if the vacuum decays. Most calculations suggest we are safe for an extremely long time, longer than the current age of the universe. But the anomalies raise new questions about whether unknown forces could influence that stability in unexpected ways. No one is pressing the panic button. These are highly speculative connections, but they illustrate how deeply these small deviations cut into our understanding of reality. Back in the control rooms at CERN, the machines keep running. The LHC is being prepared for Run 3 and eventual high-luminosity upgrades that will deliver even more collisions, more data, more chances to confirm or rule out these hints. Teams continue analyzing. Theorists continue calculating. Young researchers enter the field excited by the possibility of being part of a genuine paradigm shift. The human element remains front and center. Scientists who have dedicated their lives to the standard model now find themselves cautiously exploring its limitations. There is pride in what has been achieved, mixed with the thrill and anxiety of potential revolution. Conferences buzz with energy. Papers appear at a rapid pace. The field feels alive in a way it hasn't for years. Yet underneath the excitement runs a deeper current of uncertainty. What if the anomalies disappear with more data? What if they strengthen? Either outcome will shape the future of physics for decades. For now, the signals persist. The walls continue to vibrate. And the picture emerging is one of a universe far richer, more interconnected, and more mysterious than the standard model alone could describe. A universe where a fifth force might quietly orchestrate aspects of reality we have only begun to suspect. A universe where the reason for your existence might involve particles and interactions that were active in the first fleeting moments of creation and still echo today in the decay patterns of beauty quarks and the spin of muons passing through your body. That is the power of these experiments. They take us from the smallest scales imaginable back to the birth of everything, connecting the invisible world inside atoms to the story of why anything exists at all. And we are only scratching the surface. The next chapter may involve direct discovery of new particles at the LHC, or It may require entirely new machines and approaches. Either way, the quiet revolution is already underway. The physicist who first noticed that anomalous decay years ago could not have imagined where it would lead. None of us could. But that single moment of surprise in the control room has opened a door to possibilities that stretch the imagination. The universe is speaking. We are finally learning how to listen. But what it has to say next might be more profound and more unsettling than we ever anticipated. Because if a fifth force exists, and if it helped shape the matter-dominated universe we inhabit, then the story of reality is far from finished. In fact, it may only be beginning. And that realization leaves us standing on the edge of something enormous. And that realization leaves us standing on the edge of something enormous. The anomalies we have been following, from the subtle preferences in beauty quark decays to the defiant magnetic moment of the Muon, all seem to converge on one of the deepest unsolved problems in physics: the question of why the universe is filled with matter rather than being an empty sea of light. Let us travel back to the very beginning. 1 second after the Big Bang, the cosmos was an unimaginable inferno. Energy churned into matter and antimatter at staggering rates. Every particle had its evil twin. Every quark had an antiquark. Every electron had a positron. Physics demanded perfect symmetry. When matter and antimatter meet, they annihilate each other in a burst of pure energy. Equal quantities should have cancelled perfectly, leaving nothing behind but a bath of radiation. Instead, something tipped the scales. For every billion antimatter particles, there was roughly 1,000,000,001 particles of ordinary matter. That minuscule imbalance survived the Great Annihilation. From it came everything: the atoms in your body, the stars overhead, the planet beneath your feet. All of human history and consciousness traces back to that 1 in a billion victory of matter over antimatter. Scientists call this the matter-antimatter asymmetry. The Standard Model acknowledges it exists and even provides a mechanism called charge parity violation that can generate a small amount of preference for matter. But when physicists calculate exactly how much asymmetry the model allows, the number comes out far too small. Billions of times too weak to explain the universe we actually live in. The beauty quark experiments at LHCb were designed in part to hunt for stronger sources of this violation. Certain decays involving beauty quarks were expected to show significantly larger asymmetries than those seen in earlier particles. The hope was that by studying them with enormous precision, researchers could finally understand where the extra matter came from. What they found instead was something more puzzling. Not just the expected violation, but clear signs that electrons and muons were being treated differently in these decays. A direct challenge to lepton universality. A hint that new physics was interfering in ways the Standard Model never anticipated. Those same new physics effects might have been active in the extreme conditions of the early universe, producing the crucial imbalance that allowed matter to survive. The anomalies we see today could be faint echoes of processes that happened when the cosmos was still less than 1/1,000,000th of a second old. This is where the human stakes become almost overwhelming. Every time you look in the mirror, every time you feel the ground under your feet, every time you watch the stars at night, you are witnessing the outcome of a cosmic lottery won by the narrowest of margins. And the mechanism that rigged that lottery might involve forces and particles we are only now beginning to detect. The muon results add another layer to this picture. the extra contribution to its magnetic moment suggests something new, coupling more strongly to the second generation of leptons. If similar preferences existed in the early universe, they could have influenced which particles survived the Great Annihilation. A fifth force, subtle and hidden, might have been the deciding factor in the story of existence itself. Physicists have built dedicated experiments to study antimatter directly. At CERN, they trap anti-hydrogen atoms, the antimatter version of the simplest element, and measure their properties with exquisite care. So far, anti-hydrogen looks almost identical to ordinary hydrogen. Almost. Small statistical hints keep appearing at the edge of measurement precision. Hints that something might differ ever so slightly between matter and antimatter. Any difference at all would be a clue. But the anomalies in decay processes suggest the real story may involve entirely new players on the subatomic stage. Now, the philosophical weight becomes almost crushing. If our existence depends on physics beyond the standard model, then the comfortable framework we relied on for generations was never the full picture. It was a map that worked beautifully for many territories, but missed an entire hidden continent. And that hidden continent may contain the reason why you are here to hear this story. Some nights, when the data streams in from the detectors, researchers sit in the control rooms and feel the full strangeness of it. They are not just measuring particles. They are listening to the faint whispers of creation itself. The same processes that gave rise to the cosmos are still leaving traces in the collisions happening hundreds of feet underground. It is a profoundly moving realization, and for many, a quietly terrifying one. Because once you accept that new physics is at work, you start wondering what else we might have missed. What other forces or particles or symmetries remain hidden? How many more surprises does reality hold? This brings us to one of the most unsettling ideas in all of modern physics: the false vacuum. Calculations suggest our universe might not be in its lowest possible energy state. It could be resting in a metastable valley, stable for now, but vulnerable to a quantum tunneling event that would create a bubble of true vacuum. That bubble would expand at the speed of light, rewriting the laws of physics as it goes, destroying everything in its path without warning. Most estimates suggest this is extremely unlikely to happen anytime soon, on timescales vastly longer than the current age of the universe. But the anomalies raise new questions. Could unknown forces influence the stability of the vacuum? Could high-energy processes we are only now probing push us closer to the edge? No responsible scientist is sounding alarms. These are speculative connections built on hints, not certainties. Yet the very possibility forces us to confront how precarious our existence might be. The cosmos that gave rise to us could, in principle, take it all away in an instant. That thought sits uneasily alongside the wonder, because the same anomalies that hint at hidden dangers also point toward profound beauty. A universe more interconnected than we dreamed, forces and particles that might link the smallest scales to the largest questions of existence. A reality that is still unfolding, still revealing itself to those willing to look deeply enough. At CERN, the machines continue their relentless work. The LHC will soon deliver more collisions than ever before. Detectors will capture data at unprecedented rates. Teams of scientists from every corner of the world will sift through it, looking for the next clue. Some will chase confirmation of the existing anomalies. Others will search for direct production of new particles. All of them understand that we stand at a crossroads. The Standard Model has served us extraordinarily well. It remains one of humanity's greatest intellectual achievements. But it may be only the beginning of a larger story. A story that includes a fifth force, new symmetries, and perhaps answers to questions that have haunted us since we first looked up at the stars. The physicist who felt her stomach drop that Tuesday morning could not have known she was witnessing the start of something much larger. None of us can predict exactly where these hints will lead, but one thing feels increasingly clear. The universe is not finished speaking, and when it does, the story it tells may be far more extraordinary, far more terrifying, and far more beautiful than anything we have imagined so far. We are no longer just observers of reality. We are beginning to see the hidden machinery that makes it possible, and that changes everything. The final pieces of this puzzle take us into the deepest philosophical waters. The possibility that our universe is metastable. The search for a more complete theory that might finally unify all forces. The profound question of what it means to exist in a cosmos that is still revealing its secrets. The journey has brought us from a single anomalous number on a screen to the very foundations of existence itself. And we still have further to go. And we still have further to go. The journey has brought us from a single anomalous number on a screen to the very foundations of existence itself. But the story does not stop at matter winning over antimatter or the hints of a hidden fifth force. It reaches even deeper into questions that touch the stability of reality itself and what it truly means to exist in this universe. Some of the most unsettling calculations in modern physics concern something called the false vacuum. Our universe might not be sitting in the lowest possible energy state. Instead, it could be resting in a metastable valley, stable enough for billions of years, but not truly permanent. Imagine a ball resting in a shallow dip on a hillside. It looks stable. It feels stable. But if it receives the right kind of nudge, it could roll down into a much deeper valley, fundamentally changing the landscape around it. In cosmic terms, that nudge could trigger vacuum decay. A tiny bubble of true vacuum would appear spontaneously somewhere in the universe. The laws of physics inside that bubble would be different, and the bubble would expand outward at the speed of light, consuming everything in its path. Stars, galaxies, every structure, every memory, every trace of what we call reality would be erased instantly and silently, without warning. Most theoretical estimates suggest we are safe for an extraordinarily long time, far longer than the current age of the universe. The probability is vanishingly small. Yet the anomalies we have been discussing raise quiet questions in the minds of some theorists. Could unknown forces or new particles at high energies influence the stability of this vacuum? Could the same physics responsible for the matter surplus also affect whether our universe remains in its current state? These are not mainstream predictions. They are speculative connections built on hints and mathematical possibilities. No one is losing sleep expecting the vacuum to decay tomorrow, but the very existence of the idea forces us to confront something profound. Our reality might be more fragile than we ever imagined. That fragility sits in strange contrast with the incredible resilience of the scientific effort underway at CERN and laboratories around the world. Thousands of scientists, engineers, and technicians from every corner of the planet work together on these experiments. They come from different cultures, speak different languages, yet they are united by the universal language of data and discovery. The ATLAS and CMS detectors alone are among the most complex instruments ever built, weighing thousands of tons and containing millions of individual sensors. They capture the fleeting echoes of collisions that recreate conditions from the first moments after the Big Bang. The data they produce is staggering. It requires supercomputers, sophisticated algorithms, and the combined intelligence of an entire global community to analyze. And within that vast ocean of information, dedicated teams continue hunting for the faintest signals of new physics. This is not glamorous work. It involves long hours in control rooms, intense debates in seminar halls, moments of frustration when the data refuses to yield its secrets, and rare, exhilarating breakthroughs that send ripples of excitement through the entire field. Yet, it is deeply human, driven by curiosity, by wonder, by the innate desire to understand where we come from and what we are made of. The scientists at CERN are not just collecting numbers, they are engaged in a philosophical quest as old as humanity itself. What is the true nature of reality? The current anomalies have turned that quest into something urgent and alive. The standard model, for all its triumphs, now feels like a beautiful but incomplete map. The cracks appearing in beauty quark decays, in muon measurements, and in other subtle places suggest we might have been working with only part of the picture all along. This creates an existential tension in the field. Pride in what has been achieved collides with the realization that fundamental revision might be necessary. Careers built on defending the model now face the possibility of rewriting large portions of it. Yet instead of despair, many feel a renewed sense of purpose. History shows that moments of crisis in science often precede the greatest leaps forward. Think of the late 19th century, when classical physics seemed nearly complete. Maxwell's equations, Newton's laws, thermodynamics. It felt like the major work was done. Then came the ultraviolet catastrophe, the photoelectric effect, unexpected behavior of light, small anomalies that shattered the old world view and gave birth to quantum mechanics and relativity. The universe turned out to be far stranger and more wondrous than anyone had dreamed. Are we living through a similar turning point? The electroweak penguin decays, the lepton flavor violations, the muon anomaly, the hints of new forces. These feel like modern versions of those earlier cracks. Signals that our current framework, as successful as it has been, is insufficient. The possibility of leptoquarks and a fifth force does not simply patch the holes. It suggests we might need an entirely new way of seeing the subatomic world. A deeper symmetry connecting quarks and leptons. A more unified description of nature that finally begins to address the known unknowns. Gravity at quantum scales. The nature of dark matter. The origin of the matter surplus. This is both exhilarating and humbling. Exhilarating because it means the age of discovery is far from over. There are new continents of physics waiting to be mapped. Humbling because it reminds us how much we still do not know. How small our current understanding is compared to the full scope of reality. And in that humility lies a profound beauty. The realization that our existence is fragile, that our theories are incomplete, that the universe is still full of surprises, can awaken a deeper sense of wonder. It compels us to look closer, to question more fiercely, to appreciate the fleeting miracle of consciousness in a cosmos that continues to evolve and reveal itself. The story of CERN is ultimately a story about the human spirit, about our courage to confront the unknown, about our refusal to accept easy answers when the data suggests something deeper is at work, about thousands of people working together across borders in pursuit of truths that transcend any single nation or generation. The World Wide Web itself was invented at CERN to help scientists share information. The technologies developed for particle physics have found applications in medicine, materials, science, computing, and beyond. The pursuit of fundamental knowledge keeps yielding unexpected gifts for humanity. But perhaps the greatest gift is inspiration. CERN stands as a beacon of what we can achieve when we unite our intellects and resources in the service of curiosity. In a world often divided, it reminds us that the search for truth can bring us together. As the LHC prepares for its next phase with higher energies and greater luminosity, the anticipation is palpable. The upgrades will allow physicists to probe even deeper, to collect more data, to chase fainter signals. The hope is that these coming runs will either confirm the anomalies with discovery-level significance or rule them out, sharpening the path forward. Either outcome moves science ahead. The possibility of directly producing leptoquarks or other new particles grows with each increase in energy. The search for a fifth force carrier continues in multiple experiments, and the larger quest for a grand unified theory, a single elegant framework that reconciles all forces and particles, feels closer than ever. Yet the path remains challenging. The energies required push the limits of current technology. The analyses are incredibly complex. Competing theoretical ideas abound. It is a journey into the unknown, demanding patience, rigor, and courage. And through it all, the universe keeps whispering. Sometimes the whispers are quiet deviations in decay rates. Sometimes they are the stubborn mismatch in a magnetic moment. Sometimes they are the faint hints that our vacuum might not be as stable as we thought. Each whisper invites us to listen more carefully, to look more deeply, to expand our imagination about what reality might truly be. The scientists at CERN and their colleagues around the world are not deterred. They are driven by that same insatiable curiosity that has pushed humanity forward since we first looked up at the night sky and wondered. They understand that the universe is under no obligation to be simple or comfortable, but they also believe it is ultimately comprehensible. That with enough persistence, creativity, and collaboration, we can uncover its deepest secrets. This is the spirit that defines cosmo-depth as well. The willingness to confront mystery, the commitment to follow the evidence wherever it leads, the courage to embrace uncertainty while never losing our sense of wonder. The current chapter in particle physics is still being written. The anomalies may strengthen into discoveries. They may fade with more data, or they may lead us somewhere entirely unexpected. Whatever happens, one thing feels certain. The universe has more to tell us, and we are only now learning how to hear the full symphony. The final part of this story brings us back to the human meaning of it all, to the legacy of CERN, to the inspiration it offers future generations, and to the profound questions that remain as we stand on the precipice of whatever comes next. The journey continues into the heart of the unknown, toward whatever truth awaits us there. The journey continues into the heart of the unknown, toward whatever truth awaits us there. As we stand on the precipice of a new era in physics, it is worth pausing to reflect on what this all means for us, not just as scientists, but as human beings living in a vast and mysterious cosmos. The work at CERN has always been more than the search for new particles or forces. It is a testament to humanity's enduring desire to understand our origins, our composition, and our place in the grand cosmic narrative. From the control rooms buried deep underground to the global collaborations that span continents, it represents one of our finest collective achievements. The anomalies we have explored in this story, the beauty quark preferences, the muon's stubborn magnetic moment, the hints of new physics reaching into the decays and interactions we thought we understood. These are not just technical curiosities for specialists. They touch the cores of what it means to exist. They remind us that the universe is not a solved puzzle, but an ongoing revelation. That even our most successful theories can be incomplete. That reality might be richer, more interconnected, and more surprising than we dared to imagine. And in that surprise lies both terror and profound beauty. The terror comes from recognizing our fragility, the possibility, however remote, that our universe sits in a metastable state. The realization that the same hidden physics that may explain why we exist could also hold forces we do not yet fully comprehend. The humbling awareness that everything we hold dear could, in principle, be rewritten in an instant by processes far beyond our control. Yet within that terror blooms something even stronger: wonder. The wonder that we are here at all. That a 1 in a billion imbalance in the early universe allowed matter to survive. That we have built machines capable of peering into the conditions of creation itself. That we possess the intelligence and courage to question our most cherished theories when the data demands it. This is the spirit that defines the scientific endeavor, and, at its best, defines us as a species. CERN itself stands as a powerful symbol of that spirit. Born from international cooperation in the aftermath of World War, it has become a global center where thousands work together across borders, cultures, and languages in pursuit of truth. The technologies it has spawned, from the World Wide Web to advances in medical imaging and computing, have transformed society in ways its founders could scarcely have imagined. But its greatest legacy may be inspirational. It shows what is possible when humanity unites around curiosity rather than conflict. It reminds younger generations that the frontiers of knowledge are still wide open. That there are still great discoveries waiting for those bold enough to chase them. The upgrades to the Large Hadron Collider and its detectors promise even greater insights in the coming years. Higher energies, more collisions, deeper probes into the subatomic realm. The next run could bring confirmation of new particles, stronger evidence for a fifth force, or clues that point toward an even more radical rethinking of physics. Whatever the outcome, the quest will continue. Because the universe is speaking in new ways, through tiny deviations in decay patterns, through the anomalous behavior of particles we thought we understood, through the quiet but persistent feeling that there is more to reality than our current map reveals. We do not yet know exactly what the full picture looks like. Will leptoquarks be discovered? Will a new force carrier be found? Will these anomalies lead us toward a grand unified theory that finally incorporates gravity and explains dark matter? Or will they open doors to something even more unexpected? The only way to find out is to keep listening, to keep building better instruments, to keep questioning with rigor and humility. For those of us watching from outside the laboratories, this story offers something equally valuable. It invites us to marvel at the universe we inhabit, to appreciate the miracle of our own existence against the odds, to embrace uncertainty as the birthplace of discovery rather than something to fear. The cracks in the standard model are not signs of failure. They are invitations to look deeper, to think bigger, to expand our understanding of what is possible. And in doing so, we ultimately expand our understanding of ourselves. Because the search for the fundamental laws of nature is also the search for meaning, for connection, for a sense of belonging in this immense cosmos. Whether the anomalies lead to a fifth force, new particles, or an entirely new paradigm, one thing feels certain. The universe is far more interesting than we thought, and we are only at the beginning of truly understanding it. So, as the machines deep underground continue their silent work, smashing particles together at energies that recreate the first moments of creation, let us carry that sense of wonder with us. Let it remind us to stay curious, to remain humble before the majesty of reality, to never stop asking the big questions. The story of CERN, of the LHC, and of these emerging anomalies is still being written. It is a story of human ingenuity, international collaboration, and the relentless pursuit of truth. It is a story that reminds us the universe is a place of endless wonder, profound mysteries, and, yes, sometimes terrifying possibilities. But above all, it is a story that affirms our place within it. We are the universe becoming conscious of itself, and in seeking to understand its deepest secrets, we ultimately seek to understand who we are. The journey continues, dear listener, from the control rooms beneath the border, to the frontiers of theory, to the quiet moments when we look up at the stars and feel that familiar sense of awe. Thank you for joining me on this exploration at Cosmo Depth. If these questions about reality, existence, and the hidden forces shaping our cosmos resonate with you, consider subscribing and turning on notifications. There is so much more to discover together. The universe is still whispering, and together we will keep listening. Until next time, stay curious, stay humble, and remember, the greatest discoveries often begin with the smallest deviations. The walls are vibrating, and what lies beyond them may be more magnificent than we can yet imagine.